All right, we're going to get set to tackle day 2 of L'Hopital and how L'Hopital helps us evaluate the limits at indeterminate forms. Yesterday we talked about the indeterminate forms of 0 over 0. We also talked about infinity over infinity. And then we also ended with 0 times infinity. And a multiplication isn't appropriate for L'Hopital. It has to be written as a quotient. So you need to use a substitution, an a substitution, to make it into a quotient. So today we're going to look at the subtraction indeterminate form and then a couple power indeterminate forms and how L'Hopital can help us with that. So just by way of review, remember that L'Hopital's rule only works on something that is a quotient. And that quotient must have an indeterminate form. So a subtraction needs to be turned into a quotient. Then the only way to turn a subtractant into a quotient is to use common denominators. Once you've achieved common denominators, then what was a subtraction of 2 terms becomes the quotient instead. So first of all, let's show that L'Hopital's rule is needed here. If we substitute in the number 1, we'll have 1 over the natural log of 1 minus 1 over 1 minus 1. That's 1 over 0 minus 1 over 0, which is infinity minus infinity. So we have an indeterminate form, but we can't yet apply L'Hopital's rule because this is not a quotient. So we need to express this as a quotient by getting common denominators. So we'll do that by multiplying the first term by the expression x minus 1 in both the numerator and denominator. And then we'll do the same thing by multiplying the second term by a natural log of x in both the numerator and the denominator. So what we'll end up having as the limit as x approaches 1 is we'll have x minus 1 as the numerator over the common denominator expression ln x times x minus 1. And go ahead, don't FOIL, just leave it as a product, it's fine. Minus the natural log of x over the ln of x times x minus 1. And so now that we've got common denominators, this whole thing can be expressed as x minus 1 minus the ln of x over the natural log of x times x minus 1. So now that we've expressed this as a quotient, now it's appropriate to use L'Hopital's rule. I'll show you why. Because if we plugged up the number 1 in at this point, we would end up with 1 minus 1 minus the natural log of 1 over the natural log of 1 times 1 minus 1. So we'd end up with 0 minus 0 over 0 times 0, which is 0 over 0. So we have now created an indeterminate form of a quotient. So now we can apply L'Hopital's rule. So I'll take the derivative of the numerator. So the derivative of the numerator, derivative of x is 1 minus 0 minus the derivative of the natural log of x, which is 1 over x times the ln of e times the chain rule of 1. And we'll clean that all up. Now the denominator is a product. So I'm going to need the product rule as part of my L'Hopital's rule. So I'm going to need to express this derivative in the product rule form. So the natural log of x times the derivative of x minus 1, which is 1. And then x minus 1 times the derivative of the natural log of x, which again is 1 over x ln e times 1. Now let's do some big time simplifying here. There's a lot of things that we can clean up about this. We don't need the natural log of e, that's redundant. We don't need 1, that's redundant. We don't need the 0. So we have the limit as x approaches 1 of 1 minus 1 over x over natural log of x plus x minus 1 over x. Okay, that's a lot of fractions within fractions. So the best move here is to multiply everything by x so that we don't have quite as many fractions in this problem as we did before. So I'm going to multiply each term by x. So these x's will reduce, those x's will reduce, and we're going to have the limit as x approaches 1 of x minus 1 over x ln x plus x minus 1. We'll plug 1 in here. That will give me 1 minus 1 over 1 times ln 1 plus 1 minus 1. 0 over 0 again. Oh, at this point you're probably going, oh, yay. Okay, one more time. I promise it works out this last time. Okay, we still have a quotient here. That turned out to be 0 over 0. So I can do L'Hopital one more time. All right, the limit as x approaches 1. So the derivative of the numerator of the derivative of x minus 1 is just 1. The derivative of x ln x needs the product rule. And then I'm going to have the derivative of x minus 1 here, which is just 1. So while I'm at it, I'm going to do plus 1. Okay, let's do the product rule. X over, or times 1 over x, and then ln x times 1. This x and 1 over x will reduce, and so I'll just have 1 there. So I have a lot of 1s. So this is the limit as x approaches 1. The numerator is 1. The denominator is now 2. Okay, that's this 1 plus this 1, that's 2, plus ln x. And I'm going to plug in the number 1. That'll give me 1 over 2 plus ln 1, and since ln of 1 is 0, I finally get the limit of 1/2. All right, this was a doozy of a problem to start our day out with. Okay, this is really good for practicing all of our algebra. Okay, so we practiced the technique of common denominators. We practiced the technique of, right here, eliminating a denominator throughout a problem just to simplify. We practiced product rule. We practiced repeated L'Hopital's rule. So this is a great question for notes and for homework. It's not a good question for a test or quiz. It takes way too long. But the things that we practice here are good for us to practice. Okay, when you come across an indeterminate form that is a power, we're going to use a technique we've seen before when we run into things that have powers that are problems, and in that case we use a logarithm. And so again, a logarithm is going to be very useful. And so we're going to do, step first will be log, step 2 will be L'Hopital, if it's a quotient, or as a quotient of a quotient. So we're going to need to do a log first and some of the log properties that go with it. And then once we have it as a quotient, we can do L'Hopital. So here's an example where we would plug in infinity. That will give me 1 plus 1 over infinity to the infinity. That will give me 1 plus 0 to the infinity, or 1 to the infinity. That is considered an indeterminate form. So some people argue, well, 1 to any power is supposed to be 1. Why isn't this 1? Because I counter back, well, anything to the infinity power is supposed to be infinity. So which rule is right? Is it the 1 to any power rule? Is that going to trump the infinity power on anything rule? So since we have two competing rules here, that's why we consider it an indeterminate form. So we're going to do our log first. So that means we'll have now the limit as x approaches infinity of the natural log of 1 plus 1 over x to the x. And what that allows me to do is pull the x out to the front. Okay, that's one of the log rules. Okay, the property is that you pull the power to the front. So that gives me the limit as x approaches infinity of x times ln of 1 plus 1 over x. Now when I plug infinity in, I'm going to get infinity times 0, which is one of those indeterminate forms. Okay, this is not a quotient. I need to express this as a quotient. So we're going to do the substitution that we practiced the day before. We're going to substitute a for 1 over x, and then x for 1 over a. So that turns my limit into turns my limit into 1 over a for x times the natural log of 1 plus a as a approaches 0 instead of x approaches infinity. And I can write this now as a quotient, which is the whole point. So I'm going to erase this 1 over a right here in the front, and I'm going to write it as over a instead. Now I have an indeterminate form I can work with because I have the natural log of 1 plus 0 over 0, which is 0 over 0. So now I can apply L'Hopital. So this will become the limit as a approaches 0. And I want the derivative. Okay, this is my quotient I'm working with right here. The derivative of the natural log of 1 plus a, which is 1 over 1 plus a times the natural log of e times the chain rule. And then the derivative of my quotient, which is 1. So I can plug 0 into that. And when I plug 0 into that, I get 1. So I was able to solve this logarithm, or this limit, by doing a logarithm followed by L'Hopital. This is not the final answer because I used a logarithm, and so I have to undo the logarithm that I used. So my final step is to undo the log, and the only way to undo a log is with e. So we have to take what we have for our answer and apply e to that. So e to the first is my limit for this problem. It's like you take a little detour. You're like, okay, just a minute, I'm going to get off on an exit here. I'm going to get off on the exit of logarithm. And you use the logarithm to help you do the work. But if you want to get back on the highway, you're going to have to get back on the on-ramp, and you're going to have to reverse what you just did. And so you have to use an exponential to reverse that. Okay, I gave us another slide just in case we needed more room, but I went off the page that way, so hopefully you had enough room for that. Okay, here's another one. We're going to do a similar thing here with the indeterminate form 0 over 0. So when we plug 0 directly in, we show that we get 0 to the 0, which is in the indeterminate form. So we are going to apply the log first. So this will be the limit as x approaches 0 from the right of the natural log of x to the x, which allows me to pull that power to the front. And so my limit is now x times the natural log of x. When I plug this in, 0 times the natural log of 0, I get 0 times infinity, which again means I need an a substitution here. So I'm going to substitute a to be equal to 1 over x, x to be equal to 1 over a, and a will approach, well, x used to approach 0, so a will now approach infinity. I'm doing this so that I can have a quotient. That's the whole point. Oops. I am now a. Okay, a approaching infinity. So this will be 1 over a times the natural log of 1 over a. And the advantage of writing it that way is that I can take this fraction and write it as a denominator instead. And so I could put this over a and get rid of that so that I have it in quotient form. And this quotient form will give me the natural log of 1 over infinity over infinity. That's the natural log of 0 over infinity, and the natural log of 0 is negative infinity, 0 plus, which is an indeterminate form. Okay, now we're ready. We've got a quotient of an indeterminate form. So now we're ready for L'Hopital. I'm still working on a, approaching infinity. So I'm going to apply L'Hopital to this quotient here. So that'll be the derivative of the natural log of 1 over a. That's 1 over a times the natural log of e times the chain rule of 1 over a, which is negative 1 over a squared. That's a lot of fractions again. All over, thank goodness my denominator is just 1. All right, how do we clean this up algebraically? Remember that ln e is 1. And when you divide by a fraction like this, it's the same as multiplying by the reciprocal. So this would be the limit as a approaches infinity of 1 over a is just a, and then negative 1 over a squared. So I'm looking at the limit as a approaches infinity of negative 1 over a as I reduce it. So I can plug infinity directly into that. That will give me negative 1 over infinity, which will give me 0. Now, of course, one of the multiple choice answers is going to be 0. So that's going to catch the people that forget that they have to undo their log at the end, which means you have to apply an e to the value that you got. So e to the 0 is 1, which is the answer to my limit. Okay, one more. Again, another power indeterminate form. If I plug 0 into this, excuse me, I'll plug infinity into that, I'll get infinity to the 1 over infinity, and then 1 over infinity is 0. So again, I have an indeterminate form in the power, a power form. So I need to apply a logarithm. So I'll have the natural log of x to the 1 over x, which will allow me to pull the power to the front. So I'll have 1 over x in front of the natural log of x. And this is already in quotient form for me. Right? I can say this is the same as the natural log of x in the numerator and plain x in the denominator. And so I can plug infinity into that, the natural log of infinity over infinity itself, which is infinity over infinity. So I have indeterminate form in a quotient. That means I'm allowed to apply L'Hopital. So the limit notation, and I'm going to apply L'Hopital to the quotient here. So that's this term. So the derivative of the numerator is 1 over x times the natural log of e times the chain rule, which is 1, and the denominator, which is 1. So I got off pretty easy this time, and having just the limit as x approaches infinity of 1 over x is all I'm left with. So that's 1 over infinity, which is 0. And my last step is to undo my log. So e to the 0 is 1, which is the value of the original limit. So we see that L'Hopital is a very, very powerful rule to have, but there are some requirements, some restrictions on when you can and can't use it. So L'Hopital is great if your form is an indeterminate quotient form. Okay, that's just one of the requirements. It's the only way that L'Hopital's rule will work. If you use it in any other situation, if you try and use it applying to something that's not a quotient, then you've misapplied it and you'll come up with the wrong limit as your answer. So this is kind of heavy on the algebra. There's not very much calculus. The only step of calculus is the part where you actually take a derivative. Other than that, it's a lot of algebra. So I imagine you might make some mistakes with common denominators. You might make some mistakes with multiplying by the reciprocal. And that's okay. We'll work through those algebra mistakes together as long as you understand the fundamentals of the calculus part, which are the requirements for what L'Hopital's rule needs. Okay, I'll see you guys on Thursday, and we'll work through any questions you've got on this lesson. All right, hope you have a good middle of your week, and hopefully we'll be celebrating a Dodger World Series at that point on Thursday. All right, talk to you later.